Okay, so most of the time when we have a lesson where I'm like teaching you something new, okay, it'll start out with a title slide where it's talks about what unit, what lesson, and what the topic is. Okay, this one is just telling us that the kinematics is the branch of physics that describes the motion of objects without reference to the forces that cause them. Mechanics is a combination of both dynamics and kinematics, but we'll just be looking at kinematics for today. So most of the time you'll get a slide that looks like this: lesson number and the key points for the day. Okay, key points are important. They kind of tell you what parts of the notes are going to be most meaningful and what things to really pay attention to. So for today, we need to understand that the motion of objects and systems can be described in terms of displacement, time, velocity. We could add to that speed, okay, distance, vector and scalar kinds of things. Okay, and that's what point number 2 is talking about, looking at scalar and vector quantities, which is something you talked about in Science 10. And looking at velocity as a change in position during a time interval. That is also something you looked at before. Okay, that's this formula. Okay, V equals V over T. You will get a formula sheet. I just haven't printed them yet. Photocopier was down yesterday, so okay, I will get you a formula sheet here real soon. Okay, remember that displacement is a change in position, so we would have final position minus initial position over time is another way that that formula can be written. All right, so we'll be looking at that. Probably we'll get to that today because obviously this stuff is review from Science 10. Okay, so the big thing here, guys, with scalar and vector quantities is that they look at the same trip from different points of view. Okay, we have a bit of a problem in our society in that we describe distances wrong. We just do. It's a cultural thing, right? If I ask you, how far is it to Edmonton? What are you thinking right now? Yeah, most people think how long it takes to get there. There are a few who go, oh, it's this far, and they actually give me a number in kilometers, but most of us immediately go to how long does it take to get there, okay? But that's not what I asked. I asked, how far is Edmonton from here? Okay, but culturally, we tell people how long it will take to get there. And we equate how far with how long. Those are two different things. How far is distance. How long is time. Okay, they're different parts of that formula. Right? So we do have to kind of get around this kind of cultural problem that we have with describing things, because it can be a real problem in certain situations. Okay, like for example, if there's a snowstorm on Highway 2 in the middle of November. Okay, that happens all the time, right? And it's not 3 hours to Edmonton. It can be 8 or more. Okay, time is dependent on how fast you can go and how far Edmonton is from here. Okay, well, how far Edmonton is from here doesn't change unless Edmonton picks up and moves. Okay, and that's not going to happen. So, okay, the time is variable, so we don't want to use that. Okay, a buddy and I had this problem when we were backpacking one time. Okay, we'd been at the end of a long day. We hiked like 30 kilometers already, and we came across this guy who was like just bebopping up this really steep hill wearing this huge pack, army fatigues, okay, and he was just bombing, like practically running with 100 pounds on his back, okay, and we're dying, and we're going downhill. We're like, hey, dude, like, did you come from like Tumbling Falls campground? Like, were you just there? He's like, oh yeah, like 20 minutes, just 20 minutes down the trail. I'm like, oh, sweet, man, we've been waiting forever, we're thirsty, we're hungry. Okay, we've got to get to this campground so we can make something to eat and not die. Okay? An hour later, we got there. We were cursing this guy. I mean, like it was a 4-letter serenade for like 40 minutes. Okay, like where is this campground? That guy was full of you know what, and we were so angry because he told us it was 20 minutes, and he was going uphill. What we didn't consider was this is probably like a Navy SEAL who was on vacation and could run us into the ground if he so chose. Okay, he was in way better shape than these two, teachers on their summer vacation. Okay? So he was way faster than us. His velocity was different than ours, so it took him less time. Okay, but as a result, he gave us a very misleading description of where the campground was. Had he told us it's still 3 kilometers from here, we would have gone, okay, that's going to take us close to an hour. Okay, but he told us how long it took him running to get there. Right? And that's different. Right? So we want to make sure we're describing things kind of properly. Okay, So there's two different ways to describe things, with scalar quantities and with vector quantities. Okay? Scalar quantities are only going to give you a magnitude and units. Okay? Magnitude would be the measured value of whatever variable we're talking about. So if it's distance, it would be Edmonton is 320 kilometers from Okotoks. Okay? If I'm describing a vector of that, I'm describing the displacement that I would have if I drove from Okotoks to Edmonton. And then I would say that it would be more like 308 kilometers at 18 degrees east of north. Okay? I'm still describing where Edmonton is in relation to Okotoks both ways. Okay? But I'm describing that trip from different points of view. One is telling me how far did I actually have to go to get there. And the other one is telling me if you had a helicopter, this is the direction you could go and exactly in a straight line how far it would be. Okay? Because obviously it's not a straight line to Edmonton if you're following the road. Okay? The road winds and goes through little towns and things like that. Okay? Now, does that mean that a scalar quantity is less accurate than a vector quantity? Because I mean, in a vector quantity, I gave how far and what direction. Is that more accurate, the same, or less accurate? I said they were both in kilometers, right? And I rounded to the nearest whole kilometer. I said 320 and I said 308. Okay? So I measured each one to the same accuracy. They're equally accurate. One's just more descriptive than the other. Okay? So what I mean by that is when I said 320 kilometers, that was the distance. That means that Edmonton is between 319 and 321 kilometers. That's accurate to plus or minus 1 kilometer. Okay? And so is the vector description I gave. 308 kilometers at 18 degrees east of north. That's accurate to plus or minus 1 kilometer. Okay? They're equally accurate. But one has more information. It's more descriptive. All right? Because I don't want anyone to get the idea that vector quantities are always more accurate. They're not. In fact, they could be less accurate. Okay? Accuracy depends on how you measure the number. Okay, so a more descriptive description would be if I gave a vector description like we did there a minute ago. Calgary is 40 kilometers at 13 degrees west of north. Again, same accuracy, but this one gives me a direction. Okay, that's not like you could actually go in a straight line from Okotoks to Calgary. Okay, you'd have to make turns unless again you owned a helicopter. Okay. All right, everybody okay with that idea? Scalar versus vector. Okay, so scalar quantities have only magnitude. Right, so distance in kilometers, time in hours, okay, speed in kilometers per hour, right, mass in kilograms, okay, those are all scalar quantities, okay, they don't have a direction. Okay. Vector quantities would be things like velocity, okay, it would be this many kilometers per hour in this direction, displacement, this many kilometers in this direction, okay, et cetera, et cetera. Everyone all right with that? Okay, so let's compare this trip from those two different points of view, right? So if I'm going to walk from my house to Walmart, okay, I would have to follow a path that's not a straight line because I don't own a helicopter. If I did, I wouldn't shop at Walmart. I can afford to shop somewhere else, okay, because I don't own a helicopter. Right? So I can't go in a straight line. So I follow, the path system through town, take the bridge across the river, blah, blah, blah. Okay, and eventually I get to Walmart. So I start from my house. When I get to Walmart, okay, and let's just say I've walked there, okay, I've walked 4 kilometers following the black path on this picture. Okay, so I've traveled 4 kilometers. Am I 4 kilometers from my house? No, this purple line is how far I am from my house. Okay, remember, shortest distance between 2 points is a straight line. That straight line is the displacement. It's how much I've changed my position and in what direction in going from my house to Walmart. So there's the 2 different points of view on this trip. Okay, so while I had to walk 4 kilometers, I only actually end up 2.8 kilometers 38 degrees north of west from my house. Okay? So this one, okay, sorry, the black one is my distance, okay? And the purple one is my displacement, right? So one is a vector quantity, the displacement, and one is a scalar quantity, the distance, okay? But they're both describing the same trick. Okay, I'm old, so my mind doesn't work as good as it used to. When I get to Walmart, I discover I've forgotten my wallet. And I'm not going to walk through Walmart for the fun of it, okay? That's not fun. So I just turn around and go home. I walk exactly the same route all the way home. Okay? It took me a half an hour to walk to Walmart. It takes me a half an hour to walk back. Okay. On my trip to Walmart, how fast did I walk? Just on my trip there. I went 4 kilometers and it took me a half an hour. How fast did I walk? 8 kilometers an hour, right? I walked 4 kilometers in half an hour. I would have walked 8 kilometers in an hour, right? How did we do that? We went speed equals distance over time. 4 kilometers in 0.5 hours gives me 8 kilometers per hour. Okay? Simple calculation. And you guys would have done ones like that last year. So my speed in walking from my house to Walmart was 8 kilometers per hour. My velocity is going to be a different number. Okay? Because velocity is a vector quantity. It's displacement over time. And we said that my displacement was 2.8 kilometers at 38 degrees north of west. Okay? That's north of west, right? Yeah. Okay? That took me half an hour. So my velocity is 5.6 kilometers per hour at 38 degrees north of west. Notice that the vector goes along. Okay? Even though I do a calculation, the vector stays with it. Right? The vector on my velocity has to match the direction I walked. Right? It would be, if it didn't, it would be like saying I walked at 10 kilometers an hour east, but I ended up 2 kilometers north. And that's not possible. Right? So the vectors are always going to match. Okay, so now I've done that. That's my trip to Walmart. And I discover I don't have my wallet, so I walk exactly the same path home. So after an hour, I'm back where I started. How far have I gone? How far have I walked? 8 kilometers. Yeah. There was 4 kilometers there, was 4 kilometers back. I walked 8 kilometers. That's the distance I traveled. What's my displacement? 0. Okay? Remember, displacement is my change in position. And I started at my house, and I ended at my house. So I didn't change my position at all. I ended up back where I started. So my displacement is now 0. Okay? All right. What's my overall speed for the whole trip? Still 8 kilometers per hour, right? I went 8 kilometers in 1 hour, right? That's what it took me. Okay? So I went 8 kilometers per hour. What's my velocity now? 0. Okay? Velocity is displacement divided by time. And now I'm back at my house where my displacement is 0. Okay? So that can happen with a vector quantity. Okay? You might end up with 0 if you don't change your position. All right, everybody okay with those ideas? All right, so this is why the odometer in your car, the one that tells you how many kilometers are on your car, doesn't read vectors. Okay, because if it did, every time you got home, it would read, no, it would read how far it is from the dealership you bought it back to your house. It would be 0 at the dealership. It's a trick question. Very few people ever actually get that one. Everyone's knee-jerk reaction is 0. Okay. But yeah, it would always read how far it is from the dealership, which would be awesome if you wanted to put it on Kijiji and sell it. Because you could say, hey, this has only got 3 kilometers on it. That's exactly why it doesn't work that way. It has to show how far you've actually driven that car. What distance has that car gone? Okay? That's the more useful measurement. Okay, is that ringing a bell a little bit from last year? B equals D over T, and stuff like that. We're going to spend kind of today and tomorrow working on that, but hopefully that's seeming familiar. Okay, so let's look at this map here. Let's say that I'm at Seldom Inn Campground, which is right here. Okay? And I want to go to Snake Indian Falls Campground, which is over here. There's a sign just outside of of Seldom Inn Campground that says Snake Indian Falls Campground, 27 kilometers. What does that sign assume I'm going to do? Follow the path. Yeah, it's going to assume I'm going to follow the path. That is 27 kilometers along the path. Is that a scalar or a vector description? It's scalar, yeah. It says how far it is, okay? It's not giving me a direction because the path, which is the dotted line, is obviously not straight, okay? So it's 27 kilometers this way, right? You would not put a sign here that says that Snake Indian Falls Campground is 19 kilometers at 42 degrees east of north or west of north, okay? Because you can't go that way. Okay? It's like full of all manner of disaster. Cliffs, glaciers, okay, bad things that you would kill you if you tried to go that way. Right? So there's times where scalar quantities are useful. There's times where vector quantities are more useful. Okay? When we're talking about things on the ground, okay, following a road, following a path, a scalar description like distance is the most useful thing. If we're talking about piloting an airplane from one place to another, what do I want to use? I want to use a vector, yeah. Okay, and vectors are a big part of being an airline pilot, because you have to take into account things like wind. Okay, if you got a crosswind, how much is it going to push the plane off course? How much do you have to correct for that? What heading do you have to have? Same if you're, the captain of a cruise ship or something like that. There's no roads to follow. You have to put in a heading and follow that heading. So vectors are really important in those situations. Okay, if I'm in a place that I'm not familiar with. Okay, like I'm standing, in Okotoks, and somebody says, and I ask them, how far is it to Calgary? Okay, and they tell me it's 40 kilometers. I'm pretty screwed. How many choices for direction do I have? All of them, yeah, 360. Now, granted, Calgary's pretty big and we're pretty close. Probably 40 of those would get you to some part of Calgary. Okay, but if I don't pick one of those 40, I'm going to walk south. Unless I walk all the way around the world, I'm not going to get there. Okay? So, in some cases, vectors are useful. In some cases, they're not. Okay, so we talked about this here. Speed and velocity have the same relationship that distance and displacement do. They talk about the same thing from different points of view. Speed is a scalar quantity. Okay? Velocity is a vector quantity. Right? If you get pulled over by the police on Deerfoot Trail, okay, they come up and they ask you, how fast were you going? Right? Do not say 130 kilometers an hour at 10 degrees south of east, because they will have a follow-up question. Have you had anything to drink today? Okay? It's just going to go downhill from there. Just tell them how fast. They want a scalar quantity. They just want your speed, not your velocity. Okay? They're going to think there's something wrong with you and actually ask you to exit the vehicle. Okay? It goes downhill really, really fast. At least that's what it looks like on police ships. They never really fast. Okay? But I like watching other people, especially if they get tased. That's really fun. Okay? But yeah, you want to give them just a scalar quantity. That's what they're asking for. So again, it's situational, right? Okay. So yeah, as long as we understand that that's how that works, right? Now, for time, okay, and we've already said velocity is vector, displacement is vector, speed is scalar, distance is scalar. What's time? Is time vector or scalar? It's kind of a weird one, but you ever know time to go any other way other than forward? No. Okay, we don't have a direction on time, right? We don't say, well, I mean, sometimes we might say it's because we're saying it wrong, 3 hours north. Okay, but that's not how we're supposed to describe where Edmonton is, for example. Okay, 3 hours north. Okay, but time is a scalar quantity because it doesn't run in different directions. Okay, time just flows, right? Unless you have a time machine and you've proven that it can go in different directions. Okay? If that's the case, we need to talk. There are things I would change in my life. So, yeah. All right. So scalar quantities, okay, just terminology here. These are, important in that I'm going to use these terms, so you need to know what they mean. Okay, scalar quantity is any measured quantity that has only a value or magnitude, like 40 kilometers, 10 days, 400 kilograms. Okay, those are all scalar quantities. Okay, distance is a scalar quantity that measures how far an object has traveled. So anytime a question asks how far, okay, and that's important, how far means distance. It means they're asking for a scalar quantity. Okay. Speed is a scalar quantity that measures how far an object travels in a set time interval, or how fast. Okay, if something says how fast, then we're talking about a scalar quantity, speed. Okay. Vector quantities are any measured quantity that has both value or magnitude and direction. 40 kilometers forward, 3.2 kilometers, 18 degrees west of south. Okay, 20 newtons east. Okay, that's a unit for force. All right, those things are all vector quantities. Okay, or 9.81 meters per second squared down. Acceleration is a vector quantity. All right, displacement, vector quantity, which measures how far and in what direction. Okay, that's how a question would phrase it. How far and in what direction means it's looking for displacement. Okay, velocity, okay, how fast and in what direction. Okay, did this thing go? Okay, because it's a vector quantity, that measures the displacement during a time interval. All right, and then obviously these are our two formulas. Okay, here's the scalar one. Speed is distance over time. Okay, velocity is displacement over time. And I wrote a little while ago that can also be written like this: final position minus initial position over time. Okay. All right. Ringing a bell? Hopefully. Okay, so we're going to go over a few kind of really easy just questions here and to kind of review these concepts. Okay. All right, so let's say I've got this person who is initially standing 1.5 meters to the right of this Inukshuk here. Okay, so this is where they start out. That would be their initial position. A little while later, they are 3.5 meters to the left of the Inukshuk. This would be their final position. Determine the traveler's displacement. Okay, so displacement is how far and in what direction you go. And we can go final position minus initial position to do that. Okay. But one of my positions is to the right of the Inukshuk, the other is to the left. Okay, so I have to make one of them positive. One positive, one negative. Yeah, if I'm going to do this mathematically, I have to assign a positive value to something and a negative value to the other. Typically, we say right is positive and left is negative. Right? So I would say here, negative 3.5 minus 1.5. Okay? If I do that, I'm going to get negative 5. Right? Isn't it 5 meters from here to there? Right? It's 5 meters to the left, right? So I got negative 5 meters, okay? Then I go 5 meters left. That's what the person displaced themselves. They traveled 5 meters to the left. Okay? You would have done stuff like that in Science 10. Okay? Why didn't I leave it as negative 5 meters?
Because it's displacement and there's no negative displacement.
Well, I could have negative displacement if the question said your initial position is positive 5 and your initial is, well, I could then. But this question didn't give me that. It said right and left. My answer has to reflect the directions I'm given. Yeah, I convert it to positive and negative to do the math, but then I put it back into north and south or right and left or whatever it happens to be. Okay? I do that after I bring it back into that. Okay? Everybody okay with that one? Okay, I want you guys to try question 1 and question 2, okay, for right now. Okay, so take out a sheet of paper. They're very much like what we just did. They're really easy, okay? But I want you guys to get those 2 done. I'll give you a couple minutes there. right, so we're looking at number 1 here. Okay, we got sprinting drills include running 40 meters, then walking 20 meters, and these are all north. 40 meters north, 20 meters north, and then sprinting 100 meters north. All right, so if we were going to draw that out, okay, we'd have like a 40-meter long vector, okay, and we'll say that that's north. Well, actually, so let's draw it right. Okay, so 40 meters north, okay, 20 meters north, and then 100 meters north. Okay, that's roughly to scale, right? So all 3 were north, and they all add up to 160 meters north. That would be our displacement. What would the distance be? Just 160 meters, right? We don't put a direction on distance because it's scalar. All right. For question number 2, to perform a give and go, a basketball player fakes out the defense by moving 0.75 meters to the right and then 3.5 meters to the left. Okay, so I'll just draw this kind of as their starting position, and they're going to go 0.75 meters that way, and then they're going to go 3.5 meters this way. Okay, so we got 0.75. And then we got 3.5. So 3.5 minus 0.75 is going to give me 2.75 meters to the left. Okay, would be their displacement there. Okay, now number 3 I didn't ask you to do, but it's pretty straightforward. Okay, if we're building a wall, bricklayers sweep cement back and forth. If you've ever put bricks together, you have to put the mortar in between them, right? And you sweep it back and forth with the trowel. Okay, so they swing their hand back and forth 1.70 meters. So I start here, I go 1.70 meters to the right, and then back to the left, exactly the same distance. If I do that 4 times, where do I end up? Back at where I started. So my displacement would be 0. Okay, but my total distance would be
6.8.
yeah, 1.7 times 4, right? Like we're doing that 4 times. So, okay. All right. Everybody okay with that? Okay, so pretty straightforward stuff. Okay, so we'll look at a few of these here and kind of see how we do. Obviously, the 2 categories, okay, that all of our measured values fit in are scalar and vector. Okay, so that's question number 1. Okay, distance and displacement are examples of 2 things that measure the same trip from the scalar and vector points of view. Okay, one gives you a magnitude, the other gives you a magnitude and direction. Okay, number 3 is something we didn't talk about. What's the importance of a reference point? Well, if I go back to this question about the give and go, a reference point is pretty important because I need to know kind of where I started so I know where to measure where I ended up at from. Okay, it gives me an idea, kind of an initial position. Okay, that initial position helps me with my final position to get the displacement involved. Okay, I want you guys to try number 4. All right, I want you to try and draw this seating plan. Okay, using those statements. See how you do on that. I'll give you a minute or 2 there. So Dolores acts as a reference point because I can't put Chad anywhere unless I measure from Dolores. So Dolores acts as our reference point here. Okay? So if we're setting this up, okay, then people go, well, where's Dolores? I don't know either. I'm just going to put a D here. And everything is going to be measured from her. She's my reference point. Okay? So it says that Chad is 2 meters left of Dolores. So, okay, there's Chad, and that's 2 meters. Okay? Ed is 4.5 meters right of Chad, which means he's how far right of Dolores? 2.5 meters. Okay. Okay, Greg is 7.5 meters left of Chad. First time I did this in this classroom in 2006, I didn't have a smartboard. There's Greg. It doesn't come off. And incidentally, they haven't painted the door frame since 2006. The G there. Okay, I learned my lesson. Don't draw it to scale was the lesson from that day. Okay. All right, so we got, here's 7.5 meters. There's Greg. He's 7.5 meters left of Chad, and Hannah is 1 meter right of Ed. All right, so I was able to draw everybody's position because I had a reference point. That reference point was Dolores. So the question is there really to illustrate the importance of a reference point. Okay? If someone walks, or the teacher walks from Greg to Hannah, what is their displacement? Okay, well, 7.5, 9.5, 12, 13 meters,
Right.
Right. Okay, so we put a direction on that. All right. Give number 5 a try. A person's displacement is 50 kilometers west. What's their final position if they started, so their initial position was 5 kilometers east? Okay, might help to draw a diagram. Okay, we're going to work a lot on vector diagrams in this course, but it might not hurt to draw initial position, final position. Okay. And I would draw a reference point. Yeah. Okay, give you a minute or two on that one. So let's have a look at this. There's 2 ways to do this. They're essentially the same thing. One is algebraic, the other is diagrammatic. Okay, so we'll look at the algebraic one first. The formula for displacement is final position minus initial position. They told me my initial position was 5 kilometers east, and they told me my displacement was 50 kilometers west. Okay, so one's east, one's west. They got to make one negative. Okay, west is typically negative. Okay, and I'm trying to find their final position. So if I want to find final position, what do I do with initial position? Add it to the other side, right? We just do algebra, okay? Rules of algebra, if you want to move something, do the opposite. So my overall displacement plus the initial position will equal my final position. So that'll mean negative 50 plus 5. Okay, because east is positive. Right? Negative 50 plus 5 is negative 45 meters. Okay? That means my final position is 45 meters west. Okay? The other way you could have done that was to draw it. Here's my reference point. Okay? Here's my initial position, 5 kilometers east of that. Okay? And I end up a total of 50 kilometers west. Well, I could figure out 50 minus 5. Okay, or whatever. Right? Either way, you're going to end up with 45 kilometers west as your final position. Okay. Everybody good with that one? Okay, number 6. We'll just talk this one through. Okay, so using this seal skin racket, these 2 children are playing catch, standing 3 meters apart. The child on the right tosses the ball to the child on the left. Okay, so the ball starts here. Okay, goes to the child on the left, and then they move 5 meters right to catch the ball again. Determine the horizontal distance and displacement of the ball from its initial position, ignoring any vertical stuff. All right, so how far does the ball travel? 11 meters. Okay, remember, distance is scalar, so it doesn't care what direction the ball goes. The ball goes 3 meters and then 8 meters. Okay, that's where that was the path of the ball, right? So it's 11 meters, right? The displacement of the ball is 5 meters right. Exactly. Okay, good. Okay, and then number 7 here, we got this wedding reception, right? So relative to the bride, describe the positions of the groom, the best man, maid of honor. So this would be, okay, so relative to the bride, bride's the reference point. Okay, the groom is 0.5 meters right of the bride. Okay, the best man is 0.75 meters left of the bride. I've never seen a wedding with that arrangement. Usually all the groomsmen are beside the groom. Anyway. Okay, maid of honor is 1.25 meters right of the bride, and the flower girl is 2 meters left of the bride. Sorry, 1.5 meters left of the bride. Okay, everybody all right with that? Okay. All right, now, using V equals D over T, in case your algebra is really, really rusty. All right, simple 3-variable formula. This will be the easiest formula you get in this course. Okay, so if algebra is something that really is hard for you, this might not be the science for you. I'm just going to put that out there. Okay, because we're going to be dealing with much more difficult formulas than that. Okay, by the end. All right. So let's say I want to solve for D. What do I have to do with T? Right, multiply both sides by T. Okay, so we end up with this. Right? If you want to move something, do the opposite. What you do to one side, you do to the other. Okay, those are the simple rules of algebra. Okay, if I want to solve for time, what do I do?
Multiply it and then divide by
exactly. I can't solve for something if it's on the bottom because I'll be solving for 1 over it. Okay, so I would still move t over here, okay, and then I would divide both sides by v. Right. The way you can double check if you've manipulated something is to put the units in and see if you get the right units. Okay, the units for time would be seconds, and the meters cancel here, leaving me with seconds. Right, so I would have known I did it right. Okay, I can kind of double check it in that way. Okay. All right, we'll leave it at that because the bell's going to go here in 3 minutes. Okay, so tomorrow we'll be working on a lot of V equals D over T problem solving.